Question number 4 assesses your ability to solve for a missing leg in a right triangle using Pythagorean theorem. The other thing it's going to require that you know how to do is simplify radicals. So there's two things in here that we'll try to review. One is the Pythagorean theorem, which typically is not a problem for us. The one that is more of a problem for us is down here in simplest radical form. We're going to review what simplest radical form is, try to refresh that. Also want to give you some properties of radicals, because there are some properties of radicals that are really important that play into how we can simplify these. We've got a product rule and a quotient rule. So we'll look at those when the time comes. So first thing, if we know 2 out of 3 sides of a right triangle, we can use the Pythagorean theorem. Make sure that it is a right triangle if you're going to apply the Pythagorean theorem. This one, if we have that square in the corner, means it's a right triangle, so Pythagorean theorem is in play. So we pull up our formula, a squared plus b squared equals c squared. And then we know that we have two different missing parts. One is a leg, and the other one is the hypotenuse. If you ever have any trouble finding the hypotenuse, it's always directly across from the right angle. So what we got to be careful with is to make sure that we put the length of hypotenuse in for c. C always stands for it, so that's 12 squared equals. Now the leg can be either one, either a or b, whatever one you choose. I'm going to put it in for b. There's really no real reason I'm doing one or the other. Just kind of like to have the a squared out front. Run through our arithmetic on this. We know that a squared plus 64 would have to equal 144. We want to solve this for a squared, so we want to move the 64 over, so we subtract 64. Now if we subtract 64, that means that some number squared has to give us a value of 80. Now with that in mind, we have to get rid of squaring. So how do you undo squaring? Well, the inverse of squaring is square rooting. So a is equal to, whenever you square root, it should be the plus and minus of the number that you're taking the square root of. But because of the context of this problem, we don't have to worry about the negative part of it, because a leg will not be negative in length. So all we have to focus on is the square root of 80. And that brings me to where we normally have a little bit of trouble, and that is reducing this and put it in simplest radical form. So now I got to concentrate on this part over here. What is simplest radical form? First of all, what it means is that you'll have no perfect square factors underneath this radical sign. So underneath this square root of 80, there could be lying a perfect square that is a factor of 80. So is there a perfect square number that we can multiply to get 80? So what are perfect square numbers? That probably lends to that question. So perfect square numbers are numbers like, and I have some examples here, 1, 4, 9, 16, 25, 36, and the list continues. And it's an endless list. These are the numbers that I think of as perfect squares. So I'm going to run through some perfect squares in my mind here and say, okay, now 80 is 80 divisible by any one of these perfect square numbers. If I hit the best number that I can hit is the greatest perfect square that's a factor in here. And the biggest perfect square factor that I know of is 16. If I take 16 and I multiply it times 5, 16 times 5 is 30, carry the 3, that's 80. So I'm going to take 80 and I'm going to write it as 16 times 5. Now this can be done because we have some properties of radicals that we should be familiar with. We can always write the square of a product as the product of the square roots. So what I'm thinking of when I simplify this is the square root of 16 times 5, which is a representation of 80, could be written as the square root of 16 times the square root of 5, and I just utilize this property. It's called the product property of radicals. The reason I would write it like that is just to simply show you probably a little bit more clearly is that the square root of 16 is 4, and it's 4 times the square root of 5. So I've put this answer in simplest radical form, so I should be able to find that number back up in here, which is 4 times the square root of 5. So we're applying the Pythagorean theorem, but in the same problem, they're able to assess our ability to put things in simplest radical form. As I said, just to reemphasize, you cannot leave perfect squares underneath the radical. If you have any perfect squares under the radical, it's not in Lowest terms. Keep in mind it's similar to another strategy that you have with fractions. You wouldn't expect them to put an answer of 2/8 on the test. That is not in simplest form, so we reduce it to 1/4. The same analogy is they will not give you a square root of 80 on that ACT test. They're assessing your ability to simplify radicals. then they expect you to be able to recognize them. I can give you one alternative to what I just showed you, and this is consistent with what your other instructors have taught you before. Anytime you have to simplify a radical, you can break this down into this prime factorization. So for instance, if you don't want to look for the perfect square factor, you break it down into two factors that are easy to see. How about 8 times 10? You break these down until you get it into its prime factorization. So I'm going to keep breaking this down until all the numbers are prime. So 4 is the only thing that isn't prime now. It's 2 times 2. Bring all your other factors down that are already prime. And then as you were taught, what you're going to do is you're going to look for anything that has pairs. So every pair of factors we're going to circle down here. Any pair that we can circle of factors, what we do is we put them outside the radical sign and multiply them together. Anything that doesn't get paired up, such as the 5, gets put underneath the radical, which is square root of 5. So as you see, we have another alternative to getting our simplest radical form on this. So again, what we're doing is we're trying to review our Pythagorean theorem and the simplification of radicals.